High in the Himalayas, Indian engineers completed one of the most difficult tunneling projects in the world. At a cost of roughly 3,200 crore rupees, around $438 million, crews excavated a 9.02-kilometer highway tunnel straight through the Pir Panjal range at more than 3,000 meters above sea level. The result was the Atal Tunnel, the world's longest single-tube highway tunnel above 10,000 feet. Not just that, it also transformed a route that had been restricted by the mountains for decades, creating a year-round connection through one of India's most difficult regions. But building it meant cutting through 9 kilometers of unpredictable Himalayan rock under enormous pressure. So how did Indian engineers pull it off? And why were conventional tunneling machines too risky to use? This is how the Atal Tunnel was built. Rohtang. The Leh-Manali Highway is one of the most important road links through this part of the Himalayas, connecting Manali with the Lahaul and Spiti region and continuing north toward Ladakh. But the route faced one enormous physical barrier, the Rohtang Pass. Sitting at roughly 3,978 meters above sea level, the pass forced all road traffic to climb over the Pir Panjal range. During winter, heavy snowfall closed the route for around 6 months, cutting Lahaul and Spiti off from regular road access to the rest of the country. Food, fuel, commercial goods, medical supplies, civilian traffic, and military convoys all depended on a road that could disappear for half the year. Even when the pass reopened, vehicles still had to follow a long series of steep bends and switchbacks, and the crossing could take 5 to 6 hours through terrain that severely limited the speed and volume of traffic. This created a major transportation bottleneck, disrupting supply lines, increasing logistics costs, and leaving communities on the far side of the mountains dependent on a seasonal road connection. Engineers needed a permanent way around the Rohtang Pass, and the solution was to drive a highway tunnel straight through the Pir Panjal range beneath it. The new alignment would shorten the route by roughly 46 kilometers, reduce travel time by around 4 hours, and create a road connection between Manali and Lahaul that could remain operational throughout the year. With the route established, engineers faced the next challenge: how to excavate more than 9 kilometers through the unpredictable geology of the Himalayas, and whether a conventional tunnel boring machine could handle it. The machine. On most modern tunnel projects, a tunnel boring machine is the obvious choice. At the Atal Tunnel, engineers ruled it out completely. The reason comes down to what a boring machine actually needs to work. A boring machine is essentially a factory on rails. At the front, a massive rotating cutter head grinds into the rock. Behind it, a steel shield supports the freshly exposed walls, while hydraulic jacks push everything forward. Conveyor belts move the crushed rock back through the machine and out of the tunnel. And as it advances, crews bolt prefabricated concrete lining segments into place, finishing the structure in one continuous pass. In good ground, a modern boring machine can cover nearly 50 feet a day. That is incredibly fast for tunnel construction. But all of that speed depends on one condition. The rock ahead needs to have the same consistency as the rock behind it. The cutter head, the shield, the lining process, the thrust system, all of it is designed for predictable ground. The moment geology shifts, a boring machine is stuck. At Rohtang, the geology was the opposite of predictable. The tunnel alignment passes through the zone where the Pir Panjal range meets the greater Himalayas, and conditions inside change drastically from one stretch to the next. Tectonic faults nobody could fully map from the surface, mixed formations of quartzite and schist, and an overburden, the layer of mountain directly above the tunnel, reaching more than a mile thick in some spots. That much rock overhead generates enormous pressure, and if a boring machine jammed under it, there would be no realistic way to dig it back out. On top of all that, temperatures at this altitude swing from the 70s and 80s Fahrenheit in summer down to well below zero in winter, which adds thermal stress to any equipment stuck underground for long stretches. That kind of failure is played out on other projects around the world. In Australia, a 2,000-ton machine named Florence got stuck in hard rock on the snowy 2.0 hydropower project in May of 2024, after already being trapped for 8 months back in late 2022. In Seattle, a machine called Bertha, the largest boring machine in the world at the time, broke down in December of 2013 and stayed underground for 2 years before crews freed it. The recovery alone cost hundreds of millions of dollars and required sinking a massive access shaft from the surface just to reach the cutter head, a process that took months of engineering work before a single repair could even begin. Technical reports on Himalayan tunneling show the same pattern, with machines getting jammed or buried in squeezing ground and faulted rock. Once a boring machine stops moving in that kind of geology, the mountain closes in around the shield, and the longer it sits, the harder it becomes to free. At Rotang, with more than a mile of rock overhead and fault zones that no surface survey could fully map, that risk was too high to accept. So the engineers at Rotang made a deliberate call. They dropped the boring machine altogether and went with the new Austrian tunneling method paired with drill and blast excavation. Slower, louder, and far more labor-intensive, but it gave them the freedom to assess and respond to every single foot of rock as they uncovered it, instead of betting the whole project on the ground staying stable for 9 kilometers straight. So that is exactly what they did. Drill and blast. Construction began on June 28, 2010, when crews set off the first blast at the Manali end of the tunnel. At the same time, a second crew launched excavation from the Lahal side near the village of Telling. The two teams would bore toward each other from opposite ends of the mountain, aiming to meet somewhere deep in the middle. The new Austrian method works on a principle that sounds wrong the first time you hear it. You do not build heavy walls to hold back the mountain. You let the rock carry more of its own weight. You stabilize the exposed surface just enough to keep it from falling apart, then count on the natural arch of rock above the tunnel to do the heavy structural lifting. The whole approach depends on reading the geology in real time and adjusting constantly, and that is exactly why it worked here when a boring machine would have failed. In practice, that meant a cycle that repeated hundreds of times over the following decade. Crews used a multi-boom jumbo drill to punch a pattern of holes into the rock face, pack those holes with carefully measured explosives, and blasted a calculated volume of rock loose. Once ventilation fans cleared the dust and gases and excavators hauled away the broken rock, the freshly exposed face got an immediate coating of fiber-reinforced concrete sprayed on at high pressure, a couple of inches thick at most. The mix contained short steel or synthetic fibers that keep it from cracking under pressure the way plain concrete would. When it cures on a blasted face, it bonds into every bump and groove in the surface, filling crevices and sealing water pathways. That is like the difference between a pane of glass and a car windshield. Both can crack, but only one of them holds together when it does. That fiber-reinforced coating works the same way, spreading stress across thousands of tiny reinforcement points instead of letting a single crack peel away a slab. Through that coating, workers drilled and installed steel bolts running well over 16 feet deep into the mountain. Each bolt was a steel rod grouted into a hole and tensioned so it pulled the outer ring of fractured rock into compression against the stable mass deeper inside, something like clamping loose pages together with a binder clip. One bolt holds a modest load on its own, but arranged in a systematic pattern around the tunnel crown and walls, hundreds of them turn the natural rock into a self-supporting arch. Geologists map the fracture patterns after every blast to determine exactly how bolts should be spaced, angled, and driven for that specific section. The whole system ran on live data. Optical sensors tracked movement in the rock after every blast cycle, and engineers at the control center used those readings to recalculate the concrete thickness, bolt length, and blast charge for the next round. The project's consultants designed several distinct support classes depending on conditions: lighter support in solid quartzite, much heavier lattice girders, and wire mesh in the shear zones where rock quality dropped sharply. Every stretch of tunnel got its own custom recipe. Surveying at this altitude deep inside a mountain created its own set of problems. Engineers relied on laser alignment systems to keep the tunnel on grade and on trajectory, so that the two headings advancing from opposite ends of the mountain would meet within a few centimeters of the planned line. The margin for error on a 5.6-mile bore through shifting geology was razor thin, and a misalignment deep inside the mountain would have been nearly impossible to correct. The survey work proved accurate. On October 15, 2017, 7 years after the first blast, the two bores broke through and connected deep inside the mountain, confirming that the survey team had held the line across the full length of the drive. Workers on both sides of the breakthrough point could hear each other's drilling in the days before it happened, and when the final charge blew through the remaining rock wall, crews from both headings met face to face for the first time after years of working toward each other from opposite ends of the same mountain. By that point, the project had consumed about 14,500 metric tons of steel and roughly 237,000 metric tons of cement, and had cleared out somewhere around 50 million cubic feet of rock, all of it hauled out through the tunnel portals by truck. The finished horseshoe-shaped tunnel, wide enough for 2 lanes with raised footpaths on both sides, measured 5.6 miles from portal to portal. But the numbers only tell the clean version of the story because one stretch of that tunnel nearly stopped everything. Seri Nala. About a mile and a half from the Manali end, the alignment crossed underneath the Seri Nala, a seasonal stream running down the mountain surface 200 to 500 feet above. Engineers knew from pre-construction surveys that a geological fault existed somewhere in this zone. What the surveys could not tell them was just how bad it would be once they actually drilled into it. When crews punched into the Seri Nala fault, they hit something nobody wanted to find: a buried aquifer fed by glacial melt that had been working down through cracks in the rock long before construction ever started. Water surged into the tunnel at pressure, flooding the work area within minutes. Different technical papers on the project place the peak flow at somewhere close to 100 liters a second, with one source putting it as high as 127. That works out to more than 100,000 gallons an hour at the worst of it, enough to fill an Olympic-sized swimming pool roughly every 6 hours. And it was not clean water. Along with the flow came the leftover debris of an ancient buried riverbed, rounded boulders, cobbles, and thick clay, the kind of material a river deposits over thousands of years. The tunnel face turned into a wall of flowing mud and loose stone. Equipment was at risk of burial. The structural lining behind the face was under threat of collapse, and workers had to evacuate the heading zone entirely until the flow could be managed. For a stretch, senior engineers seriously weighed the possibility of rerouting the alignment or abandoning this section entirely, because the ground ahead looked like nothing any of them had worked through before. The first response was emergency pumping, running high-capacity pumps around the clock to pull water and slurry out of the work area. That bought time, but the flow rate never dropped. To actually push through, engineers deployed a technique called pipe roofing. They used hydraulic drills to drive large diameter steel pipes forward through the loose ground ahead of the tunnel face, arranged tightly in an arch. Packed close enough together, those pipes act as one continuous shell, a rigid canopy holding up the roof while excavation happens underneath. Ordinary cement was ruled out immediately for sealing the water, since the flow would wash it away before it could set. Instead, engineers pumped polyurethane grout under heavy pressure into the cracks. Polyurethane has a useful property here. On contact with water, it expands rapidly and hardens into a rigid foam within seconds, filling gaps, binding loose material together, and blocking the water's path. That turned the fractured, saturated rock into something solid enough to excavate underneath safely. Even with the canopy overhead and the water sealed, the pace slowed to almost nothing. Crews advanced only around 20 inches at a time, and after each short advance they stopped completely, while engineers assessed the face again before allowing the next cut. The standard sprayed concrete shell was abandoned for this stretch. Engineers switched to heavy steel ribs packed tightly together, and they changed the tunnel's cross-section from the usual horseshoe shape to something closer to circular, which spreads ground pressure more evenly around the full ring instead of concentrating it at the corners. They also closed that ring fast by installing a temporary invert, the curved floor section, immediately after each short stretch of excavation, so the structure had a complete loop of support, resisting pressure from every direction. This stretch of fault zone measured roughly 1,900 feet by most technical sources, and getting through it took close to 5 years. Nearly a fifth of the project's entire construction timeline burned through on less than a quarter-mile of tunnel. By the project's own account, conditions here were worse than anything the engineers had planned for, and of every obstacle they faced over that decade, the Seri Nala Fault Zone posed the greatest risk of shutting down the entire project. Winter. The underground challenges were one thing, but the conditions above ground imposed a completely separate set of constraints on the entire construction schedule. The Lahal end of the tunnel opens on the far side of the Rotang, and during winter, heavy snow makes the pass impassable from around November through April. For that window, no personnel, equipment, or materials could reach the north side by road, and crews there simply stopped work for close to 6 months every year for the entire duration of the project. That left the Manali side handling an outsized share of the work, at points responsible for the bulk of total excavation simply because the other end was cut off. Supply logistics during those months were brutal. Every piece of steel, every bag of cement, every replacement drill bit for the Lahal heading had to be stockpiled before the first snowfall. And if something ran out midwinter, there was no way to get more until spring. Conditions in spring were just as dangerous. In March of 2014, construction records point to more than 100 avalanche incidents along the access road, ranging from small slides to events large enough to bury equipment and block access for days. On October 16, 2013, a separate crisis hit near the Lahal end when around 100 feet of tunnel roof caved in. Crews stopped excavation completely and spent weeks monitoring the damage with a repeated scanning before the site stabilized enough to resume blasting. Inside the tunnel, temperatures looked nothing like conditions on the surface. While the outside dropped to negative 22 degrees Fahrenheit, the active heading zones deep inside the mountain reached as high as 107 degrees, driven by geothermal heat and the sheer weight of rock overhead. The swing between the portal entrance and the tunnel face could exceed 129 degrees, depending on the season and depth. A crew member could step into freezing wind at the mouth of the tunnel and, half an hour later, be drenched in sweat over a mile inside the mountain, working in conditions closer to a steam room than a construction site. Ventilation crews ran fans around the clock to push cooler air toward the heading, but deep inside the mountain, heat management was a constant problem that slowed shifts and drained workers faster than any altitude effect. Engineers from Strabag, the Austrian partner on the joint venture, called this the most extreme project they had ever worked, and these were people who had already built major tunnels across Europe. Specially trained rescue crews stayed on site through winter and avalanche season, and more than once, they pulled buried workers out of the snow. Every winter shutdown on the Lahal side meant restarting equipment that had been sitting frozen for months, and every spring the access road had to be cleared of new slides before a single truck could reach the north portal. The construction schedule effectively lived on a 6-month calendar, planned around snowfall and geology that controlled when work could happen at all. Below the road. Building the tunnel was one kind of challenge. Making it safe to drive through every day was a completely different one. A single tube tunnel measuring over 5.5 miles through a mountain raises an uncomfortable question. If a vehicle catches fire inside, how does anyone evacuate when there is only one tube and no separate escape route? Most long tunnels solve this by building a second parallel bore dedicated entirely to emergencies. But at this altitude and in this geology, doubling the excavation would have added years and billions of rupees to the project. Engineers solved it differently by splitting the horseshoe-shaped cross-section horizontally with a concrete slab. The upper level holds the main 2-lane roadway. The lower level, a passage a bit over 7 feet tall and about 12 feet wide, functions as an independent evacuation tunnel with its own ventilation system and airlocks at each access point. At regular intervals, roughly every 500 meters, trapdoors in the road surface open straight down into that lower passage. A driver caught in smoke a few miles inside the mountain never has to run for a distant portal. They pull open a hatch in the road, drop into a sealed corridor with its own clean air supply, and walk out through a completely separate exit. The entire lower passage runs the full length of the tunnel, portal to portal. The escape passage has its own lighting, its own communication system, and its own airflow, all independent of the roadway above. Designers describe this layout as remarkably compact for India, since most tunnels of this size build the escape route as a fully separate parallel bore at far greater cost. The ventilation system uses a semi-transverse design. Large fans at both portals push fresh air through an overhead duct extending the full length of the tunnel, and fire dampers spaced along that duct can isolate specific zones during an emergency, pulling smoke out of the fire area while keeping breathable air flowing in the evacuation passage below. Pollution sensors track air quality around the clock, and when readings drop below acceptable levels during normal traffic, the system automatically ramps up airflow. Beyond that, fire hydrants line the tunnel at regular intervals, tied into a ring main that loops through the lower egress passage so the water supply stays intact even if fire damages the infrastructure above. CCTV cameras feed live video back to monitoring rooms at both ends, and an automatic detection system flags vehicles that stop or slow unexpectedly. Emergency telephones connect straight to the control center. Loudspeakers broadcast announcements the length of the tunnel, and all of it feeds into a single SCADA platform, letting operators at either end monitor and control every system inside the mountain from one screen around the clock every day of the year. After a decade of blasting, flooding, freezing, and rebuilding, the tunnel was ready. October 3rd. On October 3, 2020, Prime Minister Narendra Modi inaugurated the Atal Tunnel, and the barrier that had cut off the Lahaul and Spiti region for 6 months every winter was gone. The route from Manali to the Lahaul Valley, which used to cross the Rohtang and take 5 to 6 hours in good conditions, now runs straight through the mountain in about 45 minutes. The tunnel shortens the distance by around 29 miles, handles up to 3,000 cars and 1,500 trucks a day at a speed limit of 50 miles an hour, and stays open 365 days a year at just over 10,000 feet above sea level. For communities on the far side of the Rohtang, that ended generations of seasonal isolation. Farmers can move crops to market year-round now instead of watching produce spoil while the pass stays buried under snow. Patients can reach hospitals in Manali without waiting for helicopter availability. Children can sit exams without weather wiping out entire semesters, and small businesses that used to shut down every November can finally plan beyond a 6-month horizon. For the Indian military, the tunnel mattered just as much. The Leh-Manali Highway is one of only 2 overland supply routes into Ladakh, and when the Rohtang closed each winter, convoys heading to forward positions along the Chinese border lost their second lifeline for 6 months straight. The tunnel opened right in the middle of an active standoff with China along the line of actual control in eastern Ladakh, and year-round access through the mountain shifted the balance in India's favor almost overnight. Convoys that once took a full day over the pass now clear the mountain in minutes. A commentator in China's Global Times even acknowledged that Indian troops could reach the border faster because of the tunnel, then warned India to hold back. That single line, more than any ribbon cutting, showed exactly how much this project mattered beyond Himachal Pradesh. The final bill came in at 3,200 crore rupees, around $438 million, still under the sanctioned budget of over 4,000 crore after a construction timeline that stretched 7 years beyond the original estimates. The tunnel is named after former Prime Minister Atal Bihari Vajpayee, who first announced it in June of 2000 and laid the foundation stone in May of 2002. He passed away in 2018. 2 years before his idea finally opened to traffic. What do you think was the hardest part of this build, the Siri-Nala fault zone or the winter logistics? Drop your answer in the comments. Subscribe for more mega build stories.